Mark P. Otten back with you. Okay, this is your introduction to latent growth models, also known as latent growth curve models. This is the thing that I presented in my very first ever conference presentation in 2004, I believe it was, and I received a question from the audience, and the postdoc that was working in my research lab at the time, her name was Michelle Magyar. I was sitting in the front row, and I received the question, and I did not know the answer. And so I turned to Michelle, who stood up from the front row, turned around, and answered the question. And I was very embarrassed because I probably should have handled that question. But anyway, now here, many years later, I have a slightly better understanding of latent growth curve modeling. And so I will hopefully be able to answer all of your questions without having to refer to anyone else. Okay, so what is this stuff? Well, latent growth curve model in its basic definition is a structural equation model for longitudinal data. If you have more than, let's say, 2 or 3 data points going across time. A continuous DV is the foundation of this. So if you have something measured on at least 3 different occasions, and this is something that is a measured variable, but it is something that may be modeled by way of latent variable. So a latent variable now is no longer like a factor or the product of a factor analysis in the traditional sense. We're not combining different measures together necessarily to compose one latent variable that sort of represents conceptually the average or the weighted average of these components anymore. What we're doing now is we're using latent variables to represent change over time. So the measurement is the same, the math is the same, but the application is different. In this case, scores should have the same units going across time. So if they have different units, you might need to convert them to the same scale or standardize them or something like that before going forward. And also theoretically, it should measure the same construct over time because you're measuring the change of something that is the same thing going across, let's say 3 or more occasions typically. So when will you do this? Well, you might do it if you, let's say, are a young researcher. When I was a young researcher, I was looking at the motivational climate of a volleyball team across different times of a season, multiple measurements across the season. Motivational climate was like how well the team was getting along, basically, in order to be motivated to succeed. So I had multiple time points. I was looking at the trend. What was it going up? Was it going down? Was it kind of doing both? Maybe it was going up for a while, then going down. And I was modeling all of that. So in that case, data were tested at the same time interval across the season. I can't remember how many months that one was, but for example, here we have 3, 6, and 9 months. And so if you have it sort of offset like 3, 6, and 10, or 3, 4, and 8, or something like that, that might be a little bit weird to model because we're looking at linear growth curves here, at least in the basic example. So linear growth meaning like equal time intervals. So the 2 steps here are you have an initial mean and a rate of change. So the initial mean is like the baseline where the measurement starts, like at the beginning of the time intervals, and then change over time is sort of incrementally assessed as you go along the different times. And then the cool part, or one of the many cool things about latent growth curve modeling, is you can do this and then you can add in predictors, and you can do that at any time point or even multiple time points. And you can predict the initial mean or the baseline level on this particular variable, and you can also predict the rate of change. So many possibilities. Okay, so let's look at the setup here. So these are your latent variables. Again, the math is the same in terms of structural equation modeling here and latent variable analysis. The math is the same, but the application is different. So we set this up as initial status and linear change. These are latent variables. Then we have the initial status variable, and we fix the loadings of that variable to the different time points at 1 each. And so that's just by definition. That's what an initial status is. We set it up that way. The initial status then represents sort of the baseline, like I said, where the starting point for the growth model. And then for linear change, the factor loadings are fixed to 0, 1, 2, 3 for the linear change latent variable. So 0 that is the loading for time 1, 1 is the loading for time 2, and so on. And that models a linear change. And so we're going to look to see if these are like your start values. And so we're going to look to see if these start values change, and if they change too much, then our trend is not really linear anymore. If it's too far away from 0, 1, 2, 3, then we're looking at something that is not linear. So that's the initial application here, but there are many different things we can look for. So I'm going to change this to a real example that I found in the textbooks. That is alcohol use among adolescents. We're going to hypothesize, well, what would be the hypothesis here? That as you get older, alcohol use may increase, maybe to a certain point and then decrease again, but the hypothesis here that we're going to operate on is if these are all adolescent years, let's say 13, 14, 15, 16-year-olds, or something like that, then we're going to hypothesize a slight increase in alcohol use through that time period. So that's the hypothesis we'll go with. Like I said, the initial status variable represents the baseline score, in this case for alcohol use. It's analogous to an intercept in a regression equation. So that's why the loadings, I guess, are fixed to 1 for that variable. It's a starting point, so it's gonna represent like alcohol use at age whatever that first time point was. And then you're gonna see how things change from there. The linear change variable, like I mentioned, has loadings fixed to 0, 1, 2, 3 in this case, and that represents a linear change. If it was 0, 1, 2, 4 or something like that, or 0, 0.5, and 3, then you would be modeling nonlinear change, but that gets a little bit tricky to conceptualize and to link to a hypothesis often. So linear growth models are the most common. So that evenly spaced part, the 0, 1, 2, 3, or you could do like 0, 2, 4, 6, that would actually be equivalent. The evenly spaced element is the key. And you could also do a negative one, so you could do like 2, 1, 0, and that would be linear but negative. So that would be the alternative here. But we're hypothesizing positive, or I guess an increase. I was going to say positive change, but that implies that drinking more alcohol is a positive thing when you're adolescents. I don't know if that's a positive thing. Anyway, I meant a positive trend, meaning like an increase in alcohol use. Okay, so if the time 1 loading equals 0, this sets the starting point at 0. If the time 1 loading is 1, then it sets the starting point at 1. So the initial status factor is based on that time 1 measurement. That's sort of a formality or a finer point of this. As long as you have that linear change in there with the equal increments, then you're modeling this appropriately. So then you got to think about this covariance here. So as a possibility, so we might have initial status and linear change co-varying or correlating as part of our hypothesis. What that would mean in this case is that the more alcohol use you have in year 1 is going to cause you to grow faster over time. Right, because a faster growth is a larger value for that linear change. So, so an adolescent who has a higher baseline level of alcohol use at the beginning might increase faster. And so, if that is hypothesized to be true, then we add in a covariance there. If we don't have a hypothesis, suppose somebody's higher level at the beginning is, well, we don't really know if they're going to grow faster. Yeah, they were high at the beginning, but we don't know. Maybe they're actually going to decrease more because they're at such a high level to start with. We don't know, right? So if we don't know, then we don't include this covariance. So that's optional. And then in the last video on multiple group models, we talked about the existence of a mean structure. This is also, and then Jody Ullman was like, yeah, so mean structures are usually in the context of multiple group models. Well, they're also in the context of latent growth models. What that means is that we can add in a mean for our initial status and then a mean for linear change, and these are going to be informative. So the mean for initial status is the average initial level of alcohol use. This is like in year 1 across our sample according to our model, and then the linear change mean is the average year-to-year increase. So basically what we're doing is we're creating a model with a intercept and a slope. It's kind of like a regression line, but in this case it's a latent growth line. And what that is doing is it's giving us a line of prediction to then compare to our actual values. And thus judge our model for quality. Error terms, this is another optional thing, so we might say that the leftover variance at time 1 is related to the leftover variance at time 2 because those two time points are next to each other. That's, I don't know, usually not included up front, but you could. You might look at a previous latent growth model. Suppose you've created one and then you have like a past research article that has included one as well, and then that past research article included these error covariances or error correlations, then you could include it based on their previous theory there. But this is also something that you can also add with an LM test at the end. You might leave these out and then add them in later. But these are sort of things that might remind you of different, so I mentioned regression. It also might remind you of a repeated measures ANOVA. Suppose you have 3 time points and you're looking at the means of those 3 time points and you're trying to figure out if there's a difference between means. Well, this is just sort of the next, I say it's much cooler than repeated measures ANOVA because you can look at these things like error terms correlating and relationships between means and changes over time and things like that. So it's next level stuff. Okay, so here's our model. I've added in the mean there at the top, which is again, it's like a constant. The 1 in the triangle represents a constant, and what the constant does is it allows you to estimate the mean for your latent variables, in this case initial status mean and linear change mean, and then that's going to be represented by those arrows there, those regression coefficients. Leading from the 1 to each latent variable. I also have the correlation or covariance in there between initial status and linear change, presuming that, let's say, if someone is at a higher level of alcohol use at year 1, then maybe they're going to change a little bit differently, maybe more quickly over time than someone who's at a lower status. Okay, so just showing you the possibility of error correlations here as well, or covariances. I'm going to leave those out for simplicity. Like I mentioned, you could put those in, though, because consecutive time points are, I don't know, there's some theory to suggest that maybe time 1 is more similar to time 2 than it is to time 3, and it's leftover variance. But anyway, we'll leave those out for now. Let's look at the standardized solution. Standardized solution will give us, well, less than usual. I think normally the standardized solution gives us all of the things that we want to see in terms of the coefficients. Here we just see one that's particularly interesting, and that is initial status correlating negatively with linear change. So that's like the higher you were on alcohol use at the beginning, year 1, actually the faster you decline in alcohol use over time. So that's that one. And then you get the residual variances down there at the bottom as part of the standardized solution as well. But there's other things that we can look for that are equally, if not more interesting from a latent growth curve model. So we need to look more at the unstandardized solution as well. That's going to give us our means. So if we look at the unstandardized regression coefficient pointing from the constant to the initial status latent variable, we're going to get 2.29, and that is on the scale of alcohol use. Number of beers per hour. No, I forgot what it was. But anyway, that's an initial status on alcohol use, probably drinks per week. I don't know, something like that. Then for linear change, you're going to get a mean as well from the unstandardized solution, and that is 0.22. So overall, there is a positive trend. The amount of alcohol use over time across the whole sample is going up slightly. And so we can model this then, or graph them on the board. Well, we don't have a board, but we can do this in class. The observed values and the expected values, or the observed and predicted values, I should say. So the predicted values is kind of like your regression line. In this case, though, it is a latent growth trend, latent growth model, and that is 2.29 at year 1, 2.51 at year 2, and so on. That's according to the model, and those are going to be equally spaced, right? So 2.29 was our, where does that come from? That's our initial mean here, initial status 2.291. That goes in for year 1, and then the 0.22, that's your mean for linear change. You add that in each time. So 2.29 plus 0.22 gives us 2.51 for year 2, and then you add 0.22 again, you get 2.73 for year 3, and so on. If that makes sense. So you take those two means that you get, and you can make a predicted line that's a linear trend over time. And then you go back and you look at your actual data, and so this is kind of like a comparison of your data to your model. And so if this is if these values are close to each other, that means that the trend is relatively linear and that your model is a accurate or it is closely resembling your data. And so in this case, it looks like it is. The differences from the observed column there to the predicted column are relatively small. And so we can say that our model is doing a pretty good job, it looks like, so far. Okay, so talking about comparing a model to your data might remind you of chi-square tests that we've done in the past. This is what the chi-square test represents, is a comparison of our model to our data to try to see if our model is well-fitting. And so we resume with degrees of freedom calculations here, which you have to include a couple more things, in particular a count of the number of means, which is a little bit, I don't know, like you just have to know that a mean here is available to be estimated for each measured variable, even though we're not measuring means specifically 4 times 1, 2, 3, and 4 each. We could if we wanted, and so then that becomes 4, which is the number of measured variables, which is also equal to p in this case, which is included in the p times p plus 1 over 2. And then the plus 4 at the end is for 4 measured variables, or 4 means for those measured variables, should we have decided to calculate them. So we get 14 in this case, and then we have a number of parameters calculation that is 9. That's the number of betas plus the number of r's, or covariances, plus the number of variances. The note here is that a variance is estimated for each measured variable as well, and also for each latent variable. So 6 variances. If we look back at the model, there's 4 measured variables, 2 latent variables, so a total of 6 variances. Then we have that one correlation or covariance in the middle there between initial status and linear change. That was our R. And then the 2 betas are the 2 regression coefficients from the constant leading to initial status and linear change. So you just have to count up all the stuff, all the parameters that you're estimating. So you get the 14 here for number of data points, and then you get the 9 for number of parameters. And then you can move forward to get your degrees of freedom. 14 minus 9 equals 5. If you want to review that with me at some point, I went kind of fast through that, I think, so just let me know. We can sit down and figure out our degrees of freedom, update our degrees of freedom calculations for latent growth models. Meanwhile, with 5 degrees of freedom, chi-square test 8.16 is given to us by R with a p-value 0.15. Remember, a p-value greater than 0.05 is a suggestion of good fit when you're talking about SEM. So this is a good fitting model since the test is not rejected. Comparative fit index is amazing. Root mean square error of approximation, not too shabby either. So our model fits well, and that just means that we have hypothesized a linear trend here, and we got one. We got one approximately that fits our data. All right, now on to step 2, something that might add a little more value to our growth model, and that is adding in predictors. And there's lots of options here. We can add in predictors that predict at time 2 only, or predict at time 4 only, or predict at all time points. There's lots of things we can do with this. When we do it, we got to make sure that we include them in the mean structure, which means that we are estimating means for those predictors as well as part of the model. That's just to do so so that we can properly connect them to our latent growth model. And then also adding them in as IVs is typically what the use is. That's typically why we add in predictors in the first place, is we're predicting our initial status and linear change latent variables with them. So what do we have here for this particular model? We're adding in gender and we're adding in family status. Gender is 0, 1, where female is 1 and male is 0. And then family status is 0 for single parent family and 1 for 2-parent family. So here is our latent growth model without the predictors in there, and then watch what happens when the predictors come in. I tried to be as artistically clean as possible when putting in all those arrows. Okay, so let's break this down a little bit. Before we just had the constant there predicting initial status and linear change to give us our means of those two. Now we have gender and family status in there. Those are hypothesized to influence initial status and linear change. And so we add them in, and then we add in arrows pointing from the constant to them as well. So that constant is now pointing to 4 things, right? Initial status, linear change. It's also pointing to gender and family status. Gender is now predicting initial status and linear change. So we might make a prediction that is something like male adolescents are more likely to drink more alcohol at year 1. That would be the relationship with initial status. And male adolescents are also more likely to increase over time in their alcohol use. That would be predicting linear change. Family status, let's say someone from a single-parent household may be more likely to engage in alcohol behavior at year 1 and also more likely to change more quickly over time, increase, let's say, over time more quickly. Those could be hypotheses that represent those predictions there. So there's a little bit of depth to it, right? We're hypothesizing more than just, hey, males drink more alcohol. It's, well, they might drink more alcohol at year 1, but they also might change more quickly over time. Same thing with the family status variable. The remaining arrows there at the top in the lighter blue are the correlation between gender and family status. So I don't know if there's a real hypothesis that might support that, but that would be like female adolescents are less likely to come from a single-parent household, something like that. And then we have that correlation between initial status and linear change, which I put as a, so that initial status and linear change are now dependent variables, right, being predicted by actual other IVs, gender and family status, in addition to the constant. So now there are arrows that represent leftover variance for those DVs, and so I'm correlating those instead of correlating just the initial status and linear change variables as before. So that's why there's that additional long arrow that goes around the top of the diagram there. That's what that is. So, okay, so let's look at the numbers. This is our standardized solution. So before, the standardized solution pretty much just gave us the correlation between initial status and linear change, and that was it, except for the residual variances. Now we have a lot more numbers to work with. So that 0.49 is still very similar to what it was before, 0.49 negative, relating initial status to linear change, meaning that actually if you are higher at year 1 on alcohol use, you're decreasing more, or you're more likely to decrease in your alcohol use over time. What are the other numbers here? Well, we have nothing, gender is not related to anything significantly, not related to initial status. There is a positive coefficient there representing gender and the linear change variable, but it's not significant. For family status, we have 0.12, not significant with the change variable, but there is a relationship with initial status that is negative. So if you're if you're in a two-parent household, you are less likely, or your initial status for alcohol use is lower. You're less likely to drink alcohol if you're from a two-parent family at year 1, but it's not related to change over time. So that's kind of interesting, right? That's a sort of a nuanced conclusion to what being in a single-parent household really means as far as its relationship with alcohol use. So that's something. That's the value of a latent growth curve model is demonstrated well by that negative 0.24, right? Because it's like, well, family status is related to alcohol use, but only at year 1, and then change over time, there's no significant relationship. So maybe during adolescence, the lack of a second parent is not as impactful, something like that. I don't know. I'm not a developmental psychologist. We'll leave that conclusion to Scott Plunkett or Holly Tanyan or someone like that. Anyway, okay, so the unstandardized solution, as I mentioned before, does hold a lot of value when it comes to latent growth models. It does again here. These unstandardized values are the means of our variables, right? So for gender, we have a 0.573. That just suggests that there were slightly more, 57% of the sample was female, something like that. And also here, 55% of the sample had two-parent, was from a two-parent household as opposed to a one-parent household. You could just get those with descriptives as well. Okay, so those are less interesting. What's more interesting here is the recalculated initial status and the recalculated linear change variable means here. So these are actually no longer means. These are intercepts for the regression equation, and the means are a little bit different now. So this is a 2.49, which represents the intercept for the regression equation, and this is the 0.159 for linear change. So what happened here? Well, To get the means now, we need to do a little bit more algebra, and we need to look at the indirect effects. So this is what the unstandardized solution looks like more completely with regard to gender and initial status. So in this case, the constant is still predicting initial status, right? But it's also predicting gender, which then predicts initial status. It's also predicting family status, which then, so it's like part of a multiple regression now, if that makes sense. So then the direct path from that constant to initial status is no longer just the mean. Now we have to do something with these values in order to translate them to get the mean. Again, there's some algebra behind this, but here's what it looks like. You're combining that direct effect with the indirect effects, and so the 2.493, where did that come from? That's the direct effect of the constant on the initial status latent variable. That was the intercept that I just showed you. So we start with that. Then we add in the 0.573 times the 0.011. Where did that come from? Well, that's the 0.573 there from the constant pointing to gender times the 0.011, gender pointing to initial status. So that's like a multiplication that is representing an indirect effect of the constant on initial status. So much work to just get a mean. Okay, and then 0.554 times 0.377. That's the other indirect effect there, 0.554. Constant to family status, and then 0.377. That's a negative, actually, family status to initial status. Okay, so we're doing some multiplications there. I don't think the negative for the 0.377 there is visible for some reason on the video screen there, but anyway, it should be negative. And it's 2.29 is the end result for our mean. Then we do the same thing with the unstandardized solution for the linear change variable. Some of these numbers are the same, some of them are different. So we have the following: 0.159 is the direct effect, 0.573 times 0.065 is your indirect effect going through gender, as you see there. 0.554 times 0.044 is the indirect effect going through family status, as you see there. You're adding in those terms again, and you're getting a 0.22, which is actually the same as before. So you're just trying to get kind of what you got before, which is an accurate estimate of the linear change mean. And why did we do this? Well, we modeled it first without the predictors, and so we kind of knew what we were getting originally. But then sometimes when you do these models, you actually start with the whole thing first, right, with the predictors in there from the beginning. And so when you do that, you kind of have to go back and make sure you do this algebra to get the means back. But anyway, once we have them, we can look back and do another model to data comparison. Here we have a chi-square test that again is suggesting good fit. So even though some of those regression coefficients pointing from predictors to the latent variables were not significant, our test is still suggesting good fit, and that's probably because again we have a strong linear relationship here that alcohol use is growing linearly over time on average. So that's going to provide us with a strong model still. Comparative fit index and RMSEA both suggest good fit still. All right, so other cool stuff you can do to finish off. First of all, hopefully you saw some benefit to latent growth curve modeling as we went through that example. You can see how you can do different things with predictors. You can maybe look at the linear change as your primary focus of a growth model, or you can look at the predictor relationships, or you can do both in connection. And usually there's some reason to do both in connection, and so that's what how latent growth curve models come together. But anyway, other things you can do, you can add in time varying predictors. So like gender and family status for us were static for our sample. But you might look at something that changes over time as well. You might look at alcohol use and drug use, and then you might try to connect those and then have a double growth model where you have alcohol use over time and then drug use over time, and then you could correlate those with each other, or you could have gender predicting drug use but not alcohol use. I mean, there's so many possibilities, right? You could do two LGMs in the same model there, drug use and alcohol use, compare them to each other. So that's a possibility. You can also do, you could have drug use at time 1 predicting alcohol use at time 3. I mean, you can do stuff like that. If you do something like that, it might be called an auto-regressive latent trajectory. That's a fancy term that just suggests that, like, you might have something at time 1 predicting something else at time 4. Some of these time-lagged kind of correlations or regressions might exist in your growth model. So cool stuff. If you're interested in some of the other possibilities here, or maybe you have a research project that looks at longitudinal data and you're like, I wonder if I can fit this growth model methodology to what I'm doing, let me know. We can look at it. You can also look at the Rex Klein textbook for a brief introduction and go from there.